What is additive manufacturing? Traditionally, or in the olden years, or in the 1980s, additive manufacture was done via photohardening thermoset polymer and used a setup we refer to as SLA. SLA printers use a laser and an array of mirrors to draw on the photohardening resin, which sets in place to form our layer. The layers are moved at one layer thickness and the next layer is drawn. This approach nets us with a 2.5-degree operation, essentially a series of discrete 2D planes stacked along the single vector. In manufacturing, we call this 2.5D machining, because the tool is never truly free in the 3D space while it's depositing material. This sort of arrangement is the most common approach to 3D printing in general, whether it be FDM, SLM, or SLA. There are several factors as to why this is the case. To name a few, it is incredibly simple to program, and it has very few moving parts. But in my opinion, it has one major and one minor issue. These are the need for support and overhangs, and the stair stepping caused by using planar slices. To address these issues, we need to move beyond the plane. But to move beyond the plane, we first have to redefine what a layer actually is. Firstly, let's talk about the general kinematics of a commercial FDM printer. I do this because this is the most common mode of additive manufacture we face. Think of an FDM printer like a hot glue gun, drawing layers upon layers to finally form a 3D model. This is usually done in the Cartesian sense, where the nozzle can be translated in X, Y, and Z. This is usually done by lead screws or belts driven by stepper motors. This setup is simple, efficient, and has added advantage that the nozzle is always normal to the plane. This is beneficial for a couple reasons. It helps with layer adhesion and reduces risk of collision between the head and the printed part. However, this simplicity means that it can't handle overhangs that well. This limits the design quite significantly, as general overhangs and side features like holes tend to deviate from the design due to the physical constraints of the method, unless we use things like supports, in which case we waste material and it requires post-processing. However, by adding another axis or two, we can eliminate the need for support materials entirely. Joshua Bird's video, 3D Print Anything Without Supports, covers this and much more in much greater detail, and evidently was inspiration for this video in the first place. In the video, we have four axes, which can be explained like a cylindrical coordinate frame, with an additional rotation around the B-axis, a wrist if you'd like. By having that extra rotation, we are allowed to position our head in a way that our head is once again normal to the surface we are pinning. This solves one of the biggest problems in regular 3D printing, the need for support material. However, in turn, we make sacrifice in simplicity in both mechanical and operational regards. The mechanical side is obvious: cable routing, filament routing, new motor to drive the fourth axis, but operation is where the biggest hurdle is. Normally, slicing software takes an STL file, slices it, and spits out the necessary G code in a few seconds. However, this fourth new axis introduces a new variable to account for, and the singularities that come with it. Just slicing along the z-axis wouldn't take advantage of the new fourth degree of freedom. This would mean extra complexity for little gain. That is why setups like this employ non-planar slices. Technically, a regular 3D printer can also use non-planar slicing, and there are great YouTube videos about this, which I've left in the description by CNC Kitchen and Teaching Tech. There are two main schools of thinking of this. One method is by tricking a planar slicer to slice non-planar slices. This is done by iteratively transforming our part geometry to form that is sliceable by a regular slicer, and then untransforming that G-code the slicer spat out and adding some post-processing to regain resolution. This works surprisingly well, and was a method used by Joshua Bird. The second is to cook up a slicer from scratch by dividing the model into chunks and using position and normal vectors to map a path. This technically would yield the best results, but the cooking up takes a lot of patience and budget that most people simply don't have. A personal gripe I have with 3D printing is the amount of time I have lost to sanding. And I'm not even talking about functional sanding, which I will get into, I promise, but I'm talking about purely aesthetic sanding. The stair stepping makes the part extremely ugly and cheap. Sanding, then using gap filler, and then sanding, and then painting, and then sanding, and then painting, and then priming. It takes so long, and in my opinion, it feels counter to what 3D printer companies claim: complexity for free, they say, while I say post-processing for 3 hours straight. However, I do also have more concrete reasons I dislike stair stepping. It weakens the parts along certain directions and causes rough surface textures that hinder aerodynamics. To give a combined example, an airfoil needs to be able to be both aerodynamic and experience triaxial stress. A regular 3D printed stair step geometry fails to deliver in both these counts. A non-planar approach would help significantly with the stair stepping and could even be used to better handle the stresses by better managing the layers, essentially like alternating bricks rather than aligning them. Multi-axis 3D printing is very material efficient. It doesn't require any support material after all. This makes the match made in heaven for the aerospace industry, where weight is literally priceless. Considering SpaceX roughly charges NASA $40,000 per kilogram of payload brought up to the ISS, and considering ISS is still reasonably close to Earth, one might imagine the benefits of making the best with what you have. Relativity Space proved additive manufacture has a place in the aerospace industry by launching Terran 1, an almost entirely 3D printed rocket, into space in 2023, which successfully passed the Kármán line, which is where we consider space to start. The company is also producing Terran R, which is a fully 3D printed reusable rocket, which by 2026 would be competing with the Falcon 9. This is almost sci-fi-esque, the closest we've ever come to a real-world von Neumann probe, a self-replicating space probe. How much more sci-fi can we get? So, where does that leave us? While services like JLC PCB are making 5-axis CNC machining accessible to everyone, most of us are still stuck in a 2.5D world, sanding our hands raw and peeling away waste plastic. 3-axis printing gave us complexity for free, but multi-axis printing promises functionality for free. By moving beyond the plane and embracing non-planar vector-based slicing, we stop stacking parts and start growing them. And honestly, my hands could really use the break from the sandpaper.